There is a moment at the end of every deep space mission that no amount of training can make feel routine. The engines are off. The spacecraft is falling, not drifting, not gliding, falling, toward Earth at nearly 40,000 kilometers per hour. The crew is strapped in, suited up, visor down. They have been gone for 10 days. They have looped around the moon and come back. They survived the launch, the radiation belt crossing, the deep black between worlds, and now comes the part that has killed people before. Re-entry. For minutes of controlled violence so extreme that the spacecraft transforms into a fireball visible from the ground. For minutes during which the temperature on the heat shield surface climbs to roughly 2,700 degrees Celsius, hotter than the surface of the sun's outer atmosphere, hot enough to vaporize steel, hot enough to make the air itself glow. For minutes during which the crew is decelerated from orbital velocity to near zero by forces that press roughly 7 times the weight of their own bodies against their chests. For minutes in which mission control cannot hear them, cannot reach them, cannot help them. For minutes of communications blackout. For minutes completely alone. This is not metaphor. The plasma envelope that forms around the spacecraft during re-entry physically blocks all radio communication. Every signal dissolves into noise. The engineers on the ground watch a flatline on their telemetry screens and do nothing but wait. The flight controllers who have guided this crew across the void, who have monitored every heartbeat and every system parameter for 10 days, sit at their consoles in silence. If the heat shield fails in those 4 minutes, no one will know until it is over. If you want to understand what makes deep space exploration different from everything that came before it, subscribe now. Because the universe saves its most precise cruelties for the moment you think you've made it home. The physics of re-entry from lunar distance is not the same as re-entry from low Earth orbit, and the difference is not marginal. It is the difference between a hot landing and a potentially unsurvivable one. When the International Space Station crew returns home, their spacecraft is traveling at roughly 28,000 kilometers per hour. That velocity is fast enough to be lethal without a heat shield, fast enough to generate temperatures that would destroy an unprotected vehicle in seconds. But it is a known problem. Soyuz capsules have solved it hundreds of times. SpaceX's Dragon solves it on routine missions. The engineering is mature. Orion is returning from the moon. Its re-entry velocity is closer to 40,000 kilometers per hour. That difference, 12,000 additional kilometers per hour, does not create a proportionally larger engineering problem. It creates a fundamentally different one. The kinetic energy that must be shed scales with the square of velocity. Coming in faster does not mean the shield gets 12 degrees hotter. It means the entire thermal environment changes character. The pressure waves are different. The duration of peak heating is different. The behavior of the ablative material on the shield surface, the material that deliberately burns away to carry heat with it, is different in ways that ground testing can approximate but not fully replicate. Because there is only one place to fully test what happens when a capsule hits Earth's atmosphere at lunar return velocity, you fly the mission. And you find out. The Artemis I mission flew uncrewed in late 2022, a full circumlunar test flight with a fully instrumented Orion capsule and no one on board. The spacecraft performed its re-entry sequence, splashed down in the Pacific, and was recovered. The mission was, by almost every measure, a success. But when engineers examined the recovered heat shield in detail, they found something the models had not predicted. The ablative material, a substance called Avcoat, a variant of the same technology used on the Apollo command modules, had charred and eroded in a pattern that didn't match the pre-flight simulations. Certain areas had burned away more aggressively than expected. The overall performance was within the margins required for crew safety. The shield did its job. The question was not whether it worked. The question was why it behaved differently than the model said it would. That gap, between what the physics equations predicted and what the physical object actually did in the actual environment, is where the anxiety lives. Not because the engineers are reckless. They are not. They spent months analyzing the data. They concluded the heat shield is safe for a crewed mission. That conclusion was made by people whose professional integrity and whose genuine human concern for the crew are beyond reasonable dispute. But the history of spaceflight is a history of exactly this kind of gap. Of models that were close enough, until they weren't. Of margins that seemed sufficient, until the specific conditions of a specific day revealed the edge that no one had quite located. The Artemis II crew knows about the Artemis I heat shield findings. They have been briefed. They are going anyway. That is not ignorance. It is the particular clarity of people who have looked at the data, understood the risk, and decided that going is still the right answer. Picture the 4 minutes themselves in their precise sequence. The capsule hits the upper atmosphere at approximately 120 kilometers altitude. At this point, it is still above the stratosphere, above any weather, above the world in any meaningful human sense. Contact with the atmosphere is initially gentle, a faint, increasing resistance. Then it accelerates. The deceleration forces begin to build. The crew, reclined in their seats at an angle optimized to distribute the g-forces across their bodies, begin to feel their suits tightening, their vision narrowing at the edges, their chests compressing under the weight of physics asserting itself. The heat shield begins to ablate. The material chars and gasifies and is swept away in the shockwave, carrying thermal energy away from the structure behind it. The capsule is surrounded by a sheath of superheated plasma that glows orange, then white. From the ground, from anyone positioned to see it, the vehicle looks like a meteor. A bright, moving streak of fire crossing the sky. Inside, the crew cannot see this. Their windows are facing away from the direction of travel. What they can see, if they look at the porthole glass, is an orange glow at the edges. What they can hear, above the roar of deceleration, is the structure around them responding, the sounds of metal and composite materials under thermal stress, of a vehicle working at the edge of its design envelope, of engineering holding. At about 80 kilometers, the communications blackout begins. The plasma is dense enough that no signal passes through. Mission Control watches the flatline. The 4 minutes run. What ends the blackout is not the resolution of the danger but the thinning of the plasma as the capsule slows. At roughly 60 kilometers, the sheath begins to dissipate. Telemetry flickers back. Voices return. And the first data points that appear on the ground controller screens tell them, in the compressed language of engineering parameters, whether the vehicle and the people inside it survived. Then the drogue parachutes deploy. Then the main parachutes, 3 of them, each one 23 meters in diameter, blossom out above the capsule, and the final violent speed bleeds away in the last few kilometers of descent. Splashdown in the Pacific. Recovery forces moving in. The hatch opening. 4 people who left Earth 10 days ago, who traveled farther from it than any human beings since 1972, emerge into daylight. They are examined immediately: blood pressure, neurological assessments, vestibular function, the suite of measurements that begins the process of understanding what deep space did to their bodies over 10 days. The data they carry back in their biology will be studied for months. It will inform every mission that follows, but that is later. In the moment, there is only the fact that the 4 minutes ended and the capsule held and the people inside it are alive. That is the entirety of what those 4 minutes have ever asked for, that the engineering be good enough, that the margins be real, that the gap between the models and the world be narrow enough this time. Space does not forgive the gap. It has never forgiven the gap. The fire on the launch pad in 1967, the cold O-ring in 1986, the foam strike in 2003, each of them was a gap. A place where what the system believed about itself was different from what the system actually was. The people preparing Artemis II have read every word of every accident report written from those disasters. They have built redundancies and changed procedures and created a heat shield anomaly analysis process that did not exist before Artemis I. They have done what humans do with hard-won knowledge, incorporated it, tested it, tried to make it part of the structure itself. Whether it is enough is a question that 4 minutes of fire will answer. The crew straps in. The capsule falls. The plasma closes around them like a fist. Mission control goes quiet. The universe, indifferent as always, applies its laws without exception or mercy. And somewhere in the Pacific, recovery vessels are already moving into position. Because the people who built this mission believe the engineering is good enough. Because the people who will fly it have decided that 4 dangerous minutes at the end of 10 extraordinary days is a trade worth making. Because humanity has always been willing to enter the fire if what waits on the other side is worth the crossing point. 4 minutes. All of it comes down to 4 minutes.